Hello friends, welcome back to today's class. So in the previous class we have seen your various cache operations. If you can have a look at the previous class. Okay, so we have learned the various cache operations, especially the first one to mention is regarding your cache hit. We learned what is cache hit and what are the various types of cache hits and all those things. We also learned that the cache hits are two types usually. One is read hit and another one is write hit. Okay, so this is one thing. After that we went through and we went to a next very important topic, which is called as cache miss. Okay, so we saw what is cache miss, how this cache miss happens. Okay, and there are again two types of cache misses. One is write cache and another one is read cache. So please go through the previous video if you would want a better understanding of today's class. So to move ahead from into today's class, today we will be trying to touch upon a new topic called as mapping functions. Okay, so as the name itself is telling you, mapping means what now? It will try to connect one device to another device, or you can say it will try to map the one process to another process. Okay, so mapping functions are usually they are used to coordinate between the data transfer of main memory and cache. Whatever the data transfer happens between the main memory and cache, if you want a coordination between them, you can say a manager between the data transfer is nothing but your mapping functions. Now, these mapping function usually they tell us how main memory blocks can be placed in the cache. That is, if I have any main memory data, how that could be read and stored in cache. That is determined, or that is being described using this cache function. Okay, now let us try to take a simple example. Then we'll try to see a simple example. Usually in your processor, whatever the processor you say, there the main memory is very large as compared to the cache. That's why the mapping of the blocks from main memory into the cache takes a lot of importance. The only simple reason because the main memory size is large, whereas the cache memory size is very less. Okay, now if I want to map, then what could be the problem then? Cache would get filled up very easily. Why? Because its size is less, whereas main memory has lot of data to send. Why? Because again its size is more. This was the trade-offs which I was speaking when we were speaking of the previous classes. Now, so if you consider the simple processor example, it usually consists of 128 blocks, and these 128 blocks are in cache, and in cache each word would be of somewhere around 16. Okay, then if you come back to your main memory has 16-bit address lines. It has 64,000 words and it has 4,000 blocks of 16 word size each. So you can just try to compare between them. If you try to compare between them, you will get that the main memory size is very large as compared to cache. So therefore, cache has to take the help of the main memory if the speed has to be increased. Okay, now so I hope you got the difference. The cache size is very less, but whereas the main memory size is very high. So that's why this mapping functions gains a lot of interest, or you can say lots of importance. Now we have three mapping functions. First one is direct mapping function, second one is associative mapping function, and third one is set associative mapping function. We'll try to study in detail all the three mapping functions. Okay, so to start with, the first one we have called as direct mapping system. Okay, so in this system what will happen is we need to check upon how the main memory will be mapped into the cache. That is the major thing. Okay, that means, say for example, you have a J blocks of main memory, and these J blocks of main memory has to be mapped into cache. That is the smaller cache which will be of some size. Okay, if I want to map it, then you need to take j modulo of 128. Okay. So I was telling that you need to map it into j modulo of 128. That means, just to illustrate, I am trying to tell you that, say for example, you have a j blocks of main memory. Remember, these are j blocks of main memory. Then if I want to map it into cache, it should be j mod 128. So remember this formula, friends, it is j mod of 128. That is j modulo of 128. So if you do this, then you can map your whole blocks. That means what you can do then, you can map your blocks only in the multiples of 128. That means, say for example, the first block would be block 0. The next block would be block 128. The third block would be block 256 and so on. That means in the multiples of 128. Why in multiples of 128? Because we are taking a mod function. We are taking a mod function, that is mod of 128. We are taking a mod of 128. What is j here, friends? J is the main memory. So main memory, that is main memory multiplied with mod of 128, you will get the mappings into your cache. You will be getting the mappings into your cache. Okay. So this is how you will be doing the mapping in your direct mapping. So this technique, whatever we are studying right now, is very simple, but the problem here is it is not flexible, because you can just observe here, we cannot put the whole main memory block into a cache, for which we are trying to put. Like say for example, if a program starts at block 1 of the main memory, and due to some loops it goes to block 129, then these both blocks must be stored in block 1 of the cache. So therefore there will be no continuous thing for a particular cache block position, even though other blocks are free and available. That means you are just put your first half here in block 1, and the loop where you are putting then in block 129. But you can just observe here in the diagram that from 1 to 128 all other blocks are free, but you cannot use it. That is the major problem in this. This is called as contention. So this contention is the major disadvantage of direct mapping. So this contention can be resolved by allowing the new block to overwrite the currently resident block. That means you can overwrite the previous data. If that is done, then you know what happens. You know that some data will be lost. So no replacement algorithm is required here. We will be studying shortly some replacement algorithms, but here no replacement algorithm is required because you are directly overwriting the data. Now, if you can observe carefully in the figure, the main memory is divided into 3 fields. The lower order bits select one of the 16 words in a block, and the 7th bit block address field determines the cache position. So therefore there are totally 128 in which the new block is to be stored. So the higher order 5 bits of the memory address are stored in 5 tag bits. So we call across something called as tag bits. Using tag bits, what we will be doing is, these are the tag bits. Using tag bits you can decide where is my memory. Okay, so that is very important. Next very important thing is, as the execution proceeds, as the execution moves from one block to another block, the 7-bit cache block of each address generated by the processor points to a particular block location in the cache. So each 7-bit would be showing you some other address in the cache. Okay, so this is one thing, friends. So you can clearly observe here how the whole thing is done. And very important thing is, it is not flexible. So in order to make it more flexible, we came across the next mapping system, which is called as associative mapping. So here in associative mapping, what was happening is, it was basically designed so that the mapping becomes flexible, which was not there in the direct mapping, and due to which the performance was degrading. That is, the performance was becoming less. Okay, but here in associative mapping, the method whatever we try to get here, it is nothing but here the whole main memory will be placed into any cache block position. That means we can use here any cache. Okay, and the mapping happens as shown in the figure. You can just observe the figure here. Here there is no need to identify a specific empty block, whereas in your direct mapping it was very much essential that you need to identify a particular empty block, but here it is not required, because whenever a new block arrives, it can be placed in any free cache block. Here there is no rule that after 0 or after 1 you have to use 1/29th block itself. Like you can see here in the direct mapping, after block 1, the next word will be stored in 1/29th position itself. That was the major disadvantage. That is not to be done here. You can use here any cache block position. That means you can do the mapping to any identified empty block. Okay, there is no need to free any cache block. Fine. So again here you have 12 tag bits. So using these 12 tag bits you will be identifying a memory block when it is resident in the cache. Okay, so these tag bits are very important. Why? Because we don't have the addresses right now. We are not instead of addresses, what we are doing, we are using the tag bits. So using tag bits, what we do, we can easily come to know that which address belongs to which blocks. Okay, so what happens usually is the tag bits of the address which we get from the processor are compared with the tag bits of each block of the cache, and if it is matched or if it is correct, then the block is present. So in this way, main memory block is associated with the free cache blocks. Remember, fair friends, free cache blocks. That means the cache blocks which are free, there we go on storing our data using main memory. Okay, and you can just observe here, that's why it is called as associative mapping. Okay, so you can just observe in the diagram here. One very important thing is here we require your replacement algorithms. Why we require replacement algorithms? Just pause the video and give a thought. Replacement algorithms are required to clear off the existing cache block so that you will be able to be getting some memory to store the next cache block. That is the main reason. Okay, and coming to cache, that is whether the cache is there, how it is cleaned, I hope that is cleared. Okay, now coming to the cost of this, the cost is bit higher when as compared to your direct mapping. Why? Because it needs to search all the 128 tag patterns to determine whether a given memory block exists in the cache or not. This type of search is called as associative search. So what is associative search then? It is searching all the tag patterns. It is searching all the tag patterns from 0 to 128. Then it will be deciding whether the block is present or not. So this type of cache system is called as associative cache. Okay. Now, one more very important thing here is the tag field. Okay. So what is the use of this tag field? Using tag field, you can do n number of parallel connections, and then you can get your desired addresses. Okay. So this is all about regarding your associative mapping. Next comes is your set associative mapping. There is one small change between the set associative mapping and associative mapping. So you can see here the small change is nothing but it will try to get the advantages of direct mapping, it will try to get the advantages of associative mapping, and thereby it is forming its own plant or own thing which is own location which is called as set associative mapping. Okay. Now, so whatever the blocks of the cache are grouped into the sets, then the mapping allows the block of main memory to reside in the block of a specific set. Okay, that is the blocks of main memory will be sent to the cache. That is what it means. Okay. Now in this example, we will try to take a simple example. Say for example there are memory blocks 0, 64, 128 and so on. Okay, and you need to map it into cache set 0 memory block, 1 memory block, 65 and 29. Okay, then any memory block which could be which can occupy either one of the two cache block positions, then totally there are 64 sets, and hence we have 6-bit set field address lines. Okay, so this is all regarding your set associative mapping. Not all, a short glimpse. You can just go through the diagram there. Now, what is happening in the diagram? In the diagram, it directly what it does. So we'll be selecting 4 blocks, right? We'll be selecting 4 blocks, and each set will be using 5-bit set field, okay, or 8 blocks per set using 4-bit set field. But as the blocks per set are increased, then tag bits will also increase, which in turn will increase the size of the search. I hope you are getting it. If the tag bits increase, then what will do? The number of pamphlets will increase. If the number of pamphlets will increase, then how will order this whole thing? That is the main idea. Okay. So I hope you are getting it. Okay. So this is very important, friends. Here the number of blocks per set are selected as per the requirements of the system. Okay. Now, what is better thing here is it becomes an alternate and better solution to the other two methods. Why? Because it is getting the advantages of the first and disadvantages of the second. So this is helping it to become a better method. Okay. Now, once again, yeah. In set associative, we'll be having some 2-3 things which are very much important. The first thing is you should know what is a valid bit. What is a valid bit? So the valid bit is nothing but it is a 1-bit cache block, and the first time this block is loaded from the main memory. So whenever the main memory block is operated by the source that bypasses the cache, a check is made to determine whether the block being loaded is currently in the cache. If it exists, then the valid bit is cleared to ensure that the stale data does not exist in the cache. Okay. Next thing is dirt bit. That is dirty bit. So dirty bit will tell you whether the block in the cache is accessed and modified. If it is accessed and modified, then it is called as dirty bit. Okay. That means it just indicates whether it's done or not. That is the secondary thing. If it is indicating that the accessed block is accessed and modified, then it is called as dirty bit. Okay. Now, next very important thing is these all things I hope you are clear. How the valid bit works, how the dirty bit works, how the direct associative and set associative mapping works. Very important for your internal friends. Don't leave these 3 topics. Just draw the diagram neatly, understandable. Okay. And yeah, I'm just changing the slide. And once your diagram gets clear, then it will fetch you wonderful marks. Okay. So this is all regarding your mapping. So one more small topic concerned with your mapping is your replacement algorithm. As I was telling just now that we will be having some replacement algorithms. So replacement algorithm is usually a direct mapped scheme. It is usually present in direct mapped cache, and here in direct mapped cache the position of the block is not predetermined. Okay. So therefore there will be no replacement strategy here. Okay. And when you speak of associative and associative, there exists some flexibility. Okay. And so these all things you need to do, you need to understand, and you need to come up with a small seminar. Okay. Thank you for your wonderful session. We will I hope so all of you have understood something from the today's class, and we will again meet up in the next class. Okay. See you. Thank you.